Morning everyone, welcome back. Just as a reminder, our homework 1 will be due on this Thursday. So please be prepared and submit before the class begins. Last time we stopped at the last corollary about the convergence rate when the setup is simplex. So we want to minimize our simplex. And there's one part that we didn't prove, so let me restate the claim again. So we assume the L infinity norm of the subgradient is uniformly bounded by M. And we also let x0. So to obtain the final result we claimed last time, we need to assume x0 is a special point. Okay, so in addition to the assumptions we had before, for example, the infinite norm of subgradient is uniformly bounded and we choose H in this way, we also need to assume the starting point is the minimum for the distance generating function W. And in our case, for the simplex case, W is the negative entropy. Because of the minimality here, x0 is the argmin. We have the following inequality. Remember, W is differentiable. Right, this is a minimality condition for minimizing over a constraint set, over a closed convex set. But this is the definition for the Bregman divergence, and because this part is non-negative, so the Bregman divergence is less than or equal to the difference of the two functions. And this is upper bounded by the max, this is equal to the mean. So it's upper bounded by this function value gap on the set delta n, the simplex. And because W right? Because W is a negative entropy and X is in delta N. So Wx is non-positive. It's between minus log N and 0. It obtains log N, minus log N when X is X0. Right? If you take log of 1 over N, you get minus log, and have a, which is multiplied by 1 over N, well, you have N of them, so it's just minus log N. So this gap is bounded by log N. This is a general complexity bound. This is a general convergence rate bound we had before. And now let's plug in this bound on D with log N. So obtain this bound and choosing this H, which is to balance the two terms, make them to be equal. And then we arrive at the final bound. This.
Excuse me, would you please explain the H one more time, and what is the intuition behind to take the H?
This is a function inversely proportional to H. This is proportional to H. There is a trade-off between H, right? So you need to choose the H to minimize this part to get the best bound. This is H that when you balance them, then you minimize them.
Yes.
Okay, with this, we conclude the lecture on mirror descent. Now, let's begin a new lecture.
Professor, sorry, I just have one question. Did we ever talk about why for the unit simplex the distance generating function happens to be the negative entropy? Or if it's beyond the scope of the lecture.
For example, one way to understand this is if you use active entropy, then your Brakman divergence is relative entropy, right? It's the KL divergence. And there will be a homework problem. Projection onto the simplex with respect to KL divergence is very simple. Remember that when you project onto the simplex for a point, this is just x over, right?
Right.
So this becomes very natural, just like a counterpart of the projection onto a ball in the Euclidean space. Right. This makes the projection easy and very similar to what we had before.
Thank you.
So now let's start talking about the proximal gradient method.
Excuse me. I had one question from this part. How do we know that balancing those two terms will make the trade-off at the best point?
You just want to minimize this function.
Yes.
It happens to be balancing them, but your goal is just to minimize this for any h positive. Solving this problem, you get this h.
taking the derivative from H and
Yes. So we begin with the definition for proximal mapping. This is the most fundamental concept in all the proximal methods. Given a fixed function f, it doesn't have to be convex. We define the proximal mapping for f as this. So proximal mapping it maps from Rn to Rn. So this mapping is a vector-to-vector mapping. The output is a vector. This is the argmin for this regularized problem. You augment f with this quadratic function. And this x is a fixed point here. The minimization is over u. U is also in Rn. Or in the domain of f, it's the same. And so this is for any point x. Suppose a function f, so this is, in general, this is a set. You map from a point x to a set. So this may not be unique. If the function f is closed and convex, then this function here, in terms of u, this is one strongly convex, right? And has to have a unique solution. So then, in this case, this set becomes a singleton. So this is a unique solution, because this is strongly convex in u. One famous example is when f is the L1 norm. In this case, let's multiply it with a parameter lambda. Lambda is positive. In this case, this proximal mapping is called soft thresholding. This one, the one I write here, this is for one-dimensional case. Y is just in R, but here this is X is in Rn. This is actually the proximal mapping for a one-dimensional function. So this is the proximal mapping for the function lambda times the absolute value. This is 1D, right? And here is in n-dimensional. The way to generalize this one-dimensional proximal mapping to n-dimension is just by doing this operation pointwisely, right? Because the L1 norm, this function fx, this is just the lambda times x1 plus, right? This can be decomposed pointwisely. It's pointwise sum. So you can do the operation pointwisely. This is just for one coordinate, and you do the same operation for all the coordinates and put them together. Just can candidate the vector. This is your output. And this is the 1D operation. Pictorially, this looks like, so this is minus lambda, this is lambda. This is a proximal mapping for 1D. Proximal mapping with L1 norm is quite useful for sparse optimization. When you want your solution to be sparse, and you try to use L1 norm to enforce this as a regularization. And it's also useful for low rank matrix solution. You can replace this L1 norm. So suppose this is my regularization. This is your loss function, and this is the regularization. This can, for vectors, this is sparsity, but for matrix, this is low rankness. And you can replace this L1 norm by the nuclear norm for matrix to obtain low rank solution. So before you do the L1, this kind of summation coordinately, you need to do SVD, or eigenvalue decomposition, singular value decomposition. If you do that, then this X is just the eigenvalues. It's the diagonal of your eigenvalue matrix. this theorem is quite useful because it connects the proximal mapping operator with the projection operator. This is saying that suppose there is a set Q which is non-empty, and then the proximal mapping for the indicator function of Q is the same as the projection of Q. And when the set is non-empty, closed, and convex, then this property still holds, and moreover, the proximal mapping is a singleton, because this function becomes closed and convex. The proof is very simple. This is just by definition. So the proximal mapping for indicator function, by definition, this is argmean. And we just put an indicator function here. And remember, the indicator function is 0 when U is in the set Q, otherwise it's infinity. So this is equal to and by definition, this argmean is just a projection operator.
So the norm we are using here is RO, L2.
Oh, yes. In this lecture, everything is L2.
Okay.
Only in mirror descent we will use the general distance and general norm. Okay, here, because this is infinity when U is not in Q, so the interesting case is when U is in Q. Right, this is when we prove the inequality about the partial difference. When we show the subdifferential is the same as subdifferential of an indicator function is the same as the normal cone of the set Q, we use this trick. If you want to minimize over a set, you can write it as an unconstrained problem, but by changing the objective function by adding an indicator function of the set. So then, because projection is the same as proximal mapping for an indicator function, then we have so many examples about, since we have many examples for the projection onto several sets, then we know the proximal mapping for the indicator of those sets. And some properties for projection are also true for proximal mapping. For example, you may remember the non-expansiveness of projection operator. This theorem is saying that when the function f is closed and convex, then basically you have this non-expansive property of the proximal mapping. This also holds for the projection onto a convex set Q. So the way to prove this is by use a definition of proxy mapping. Suppose U is, because this is a vector, so we let U to be the proxy mapping of X, and let V to be the proxy mapping for F at the point Y. This means, just by definition again, so from this we can say that 0 is in partial F U plus U minus X. And this is the automatic condition for this minimization. And hence, X minus U is in the subdifferential F at U. And by definition, for any point W in Rn, these two are equivalent. This is the definition for the subdifferential. If we plug in this, so because this holds for any W, let's use V as a W. Then we have FV is equal to FU and we can do the same thing for the for this optimization problem, for this proxy mapping. So then we have basically for this one, you do the following step. This is also true for any W, and now you replace W by U, right, to make them symmetric. So we have U here. This is by using W to be U. And now let's add them together. So then they will cancel, right? We get 0 greater than or equal to X minus U minus V plus minus Y plus V, V minus U. Right, now we rearrange the terms. This is just by rearranging the terms. And noting that U is prox mapping for X, this is prox mapping for Y, then we obtain this result, the first one.
Excuse me, how did you rearrange this point?
Which one?
How did you rearrange the last line?
This one?
Yes.
Just put x and y to this side and leave u and v on this side, then you have the norm square. Right. From the first claim to the second claim is just by the Cauchy-Schwarz inequality. Right? This is upper bounded by the product of this norm and this norm, and this one cancels with this one. If it's zero, then you have nothing to prove. Right? If it's zero, this is always true. Otherwise, you can cancel the norm. Okay. Any questions? This is a very quick introduction to the proximal mapping operator. There are many non-trivial examples in the book by Amir Beg, and he also has a table for many interesting cases. The theorem is saying that when the function is closed and convex, then the following property holds for any x. This is a proximal mapping for x with respect to the function f. This is a proximal mapping at the same point, but this is with respect to the conjugate function f. And the sum of the two is the same as a function at the point x. This is called Moreau decomposition. And it's quite useful to derive the proximal mapping for function f star, the conjugate function. Suppose there is a non-trivial function, some f star, some f, maybe some function g, and it's not easy to directly derive the proximal mapping for g. But you realize that g can be written as the proximal mapping, the conjugate of some function. Then using this property, if you know the proximal mapping for f, then you know the proximal mapping for f star.
So with the proximal mapping so it doesn't matter in this case because we're using L2, but would the proximal mapping for the conjugate function be the dual norm for the other proximal mapping? So the first proximal mapping would be, say, the L1 norm. Would you use the L infinity norm for the second proximal mapping?
Yeah, that's a way to derive the L infinity norm, right? Proximal mapping.
Oh, okay.
This is just a way, basically the usage of this one is to say proximal mapping for f star is x minus this proximal mapping. And if this is simple, then you can use this property to derive the proximal mapping for f star. I think we will have some homework problems. For example, the indicator function of q. This is the conjugate of it. This is the support function for Q. So if you want to derive the proximal mapping for the support function, then it's nothing but x minus the projection onto Q, right? And some other interesting example is like okay, it's the same property. So indicator function, and you take the conjugate. This is the support function for the set Q. Suppose now my Q is delta n is a simplex. Projection onto proximal mapping for indicator function is projection. So the proximal mapping for this indicator function for this simplex is projection onto simplex. But this is with respect to L2 norm, not like what we said for the KL divergence. Your distance now is L2 norm. This is different from the solution is not this simple. It's much complicated than this one, much more complicated. And it's interesting that the support function for this one, the support function is just the max of the coordinate. Suppose this is for function for point x. Then this is just max xi for the coordinates. I is between n1 and n. This is another non-trivial example. So now putting everything together, suppose I call this function a g function, right? Then I want to know proximal mapping for g. Because I realize g is the conjugate of indicator function. So by using this property, this is right. And now this is x minus prox iq x minus projection q x. So if you know the projection onto the simplex, then you know the proximal mapping for this coordinate-wise maximum function. Okay, that's the usage of this theorem.
Could you remind us how the conjugate is defined?
This is a maximum of inner product minus the function itself. And you can show that these two are equivalent by using the, you can show this is true. This is a general statement for any function, any set Q. I think this will be a homework problem. Okay, let's prove this theorem. we again let some u to be the proximal mapping for f at the point x, and this is by definition this argmin. We have seen this optimal solution gives you this condition and it's equivalent to, so from all the way from here to here, they are all equivalent, both directions. And this is saying that x minus u is in the subdifferential. Remember, this step is by theorem 2 in the last lecture. These two conditions are equivalent. X minus u, in general, this is some y. Y in the subdifferential for f at u is the same as saying that u is in the subdifferential for the conjugate function at the point y. So now this y is just x minus u. You can exchange the two. Remember that we also say that for the distance generating function, the inverse mapping is the gradient of their conjugate, right? So this is the same thing. It's just the function is not strongly convex, so this is a set, but the mapping still holds reversely. From here to here, it's also equivalent. You just do this derivation again from this part to here, right? You can still, just by following the same logic, you can still show this is equivalent to this. So from here, everything is equivalent to here. Both directions hold. And then, so we have the proximal mapping for the conjugate function at point x. Now sum them up. This is u, this is x minus u, so the summation is just x. The proximal mapping is a vector. It's the optimal solution for this problem. And the function value is called Moreau envelope. Here, f is again closed and convex, and this parameter mu is greater than 0. And this is the function value is the minimum is called the Moreau envelope. Here, mu is called the smoothing parameter. Because we are going to show this function is smooth, and the smoothness is dependent on the parameter mu. Suppose this is my function f, and so this function is convex but not smooth. Now I want to construct the Moreau envelope. So going through each point x, I'm building a quadratic function. So locally at this point x, this is a quadratic function. So let's call this function to be some fxu. Let's call it some fxu. View this x as an index, and the argument is just u. View this x as an index. So this may be my fx0 u, and at another point, I'm building another local function, right? This is fx1u. So after you have so many, this is a minimization. This is a function of u, but the index is on x. And this is a minimization over u. So we are minimizing. So the minimization should be something look like this. It's going through all the local approximations, but just the tangent to them. And this approximation, this lower approximation, is the Moreau envelope. So this will be a smooth function. At this point, this kink here, it will be smoothified. And you can show that the Moreau envelope is always below f of x. This is because the Moreau envelope is the argmean. So the Moreau envelope is less than or equal to the function value at any point u, right? And now I'm taking the u to be, so this is less than or equal to any u. And if I take the u to be x, this is equal to fx. So Moreau envelope is always below f, and it is also smooth. So the drawing is not good, but the idea is like this. You build a local approximation, and then you take the minimum. This will give you something underneath, but it's smooth. So Moreau envelope will always be a smooth function. There are several properties of Moreau envelope. Let's make them clear. First, as we said, Moreau envelope is always below the function f. And second, you can compute the gradient from the Moreau envelope. This is a simple computation, right? Pick the gradient for this one with respect to x, and use the fact the minimizer for this one is just the proximal mapping, right? By definition. So you replace u by the proximal mapping. And third, this is a 1 over mu Lipschitz continuous mapping. And hence the function, the Moreau envelope, this is 1 over mu. This is 1 over mu smooth. before we prove this smoothness, let's view another example of the Moreau envelope. This is for the convex case. You can also apply the Moreau envelope for a non-convex function. Okay, so here's an example. My function f of x this is a 1D example. This is the absolute value of x squared minus 1. So as you can see, this is a non-convex function and it's also non-smooth. By applying the Moreau envelope, okay, we can actually add another parameter for the, oh sorry, I think I missed the mu. There's no mu here. There's a mu parameter, sorry. When mu is 1, this is the proximal mapping. The solution is a proximal mapping. But in general, there's a mu. So this is the function f, and this is the Moreau envelope with parameter for example mu to be 0.2, and this is the case when mu is 0.4. And in the extreme case, this is with infinity. So as you can see, when the mu gets larger and larger, the function becomes more flattened, right? So in the extreme case, it will be a flat line. And for the kinks, these two kinks, it will be smooth. This proximal mapping, the yellow line or the white line, they are all smooth at these points. But you can never convexify the function. The Moreau envelope is again a non-convex function, but it's smooth. So Moreau envelope will only help you to smoothify the function, but not convexify the function.
Is there any theorem that says, like, if the function is convex, the envelope is convex as well, or vice versa?
Oh, sorry, yes. That's the last property I didn't mention. Yeah. Moreau envelope maintains convexity. That's a good point. And yeah, the way to show Moreau envelope is convex, if f is convex, is very interesting because so this is a function. You can also, instead of viewing this x as an index, you can also view this as a function, for example, g of ux. a function of two arguments. If f is convex, then you can show this function is actually convex in u and x, jointly convex. And so this Moreau envelope is equal to the mean of this function over u, right? So it's like a partial minimization. You keep x intact, but you minimize over u. There's a theorem saying that if the function is jointly convex, then partial minimization still maintains convexity. So that's why Moreau envelope is also convex if f is convex. Or you can argue from the epigraph. So this function is the epigraph of this function is convex because the function is convex. So the epigraph is a convex set. And if you do a projection, orthogonal projection, with respect to this parameter, right? Then the projection of the set is again a convex set. So the epigraph of this function is again a convex set. So the function is convex. This is an alternative way to show it's convex. Okay, let's prove property 3, why it is 1 over L Lipschitz continuous mapping. So by definition of a 1 over mu Lipschitz continuity, we should check whether this is less than or equal to this quantity, right? 1 over mu square x minus y square. If this is true, taking the square root, we are finished. So let's just check this inequality. This is just by the second property. This is gradient. These are gradients. By the second property, we are using the Moreau envelope. Gradient for Moreau envelope is 1 over mu x minus proximal mapping. So by definition, we have the first line. The second line is just to expand the square. In this line, the third line, we are using the property that this norm square is less than or equal to this inner product. Right, so this is less than or equal to x minus y square minus this proximal mapping difference norm square. And because this is non-negative, so we can throw it away. What's left is just 1 over mu square x minus y square. Okay, and then by definition, we have gradient is 1 over L, 1 over mu Lipschitz constant, continuous. And so the function, the Moreau envelope is 1 over mu smooth. So this is indeed a smooth function, and smoothness is dependent on mu. So mu is called smoothing parameter. Okay, now we are ready to talk about the proximal gradient method. Proximal gradient method is used for solving this kind of optimization problem where you have the objective function is a sum of two functions, f plus h. The assumption is h is closed and convex, and f is also closed and convex. Domain f is convex. We assume the function h is closed and convex, and it's also simple. Simple means the proximal mapping for h exists, and it's available to us. For the function f, we assume it's closed convex, domain of f is convex, and the domain of h is contained in the interior of the domain of f, and f is also smooth, L smooth over the interior of its domain. And also the optimal solution set x star is empty. What's more important is here, we assume f is Lipschitz smooth, it's L smooth. So for now, we just assume the function is smooth and we will work with proximal gradient method. There is also a proximal version for the subgradient method. But I think we will just mention the gradient method. The proof for proximal subgradient will be quite similar. Let's state a constant step version for the proximal gradient method. the proximal gradient method can be viewed as a generalization of the projected gradient method. Previously we assume basically we let h to be the indicator function of q, right? hx is indicator of q at point x, and that is equivalent to minimize over x in q f of x, right? And the algorithm to solve this problem is by taking the gradient step and then we do a projection onto the set q. And now, to generalize it, we make h to be any function that has proximal mapping. So projection onto h becomes proximal mapping onto h, right? So this is a concept version, constant step size. Lambda is just a constant greater than 0. And the same is saying that when the function f is, as assumed over here, it's closed convex and L smooth over its interior of its domain. And furthermore, we assume the step size is small, between 0 and 1 over L, no more than 1 over L. Assume you know L for now. Then you can show that the algorithm converges at the rate of 1 over K. This is for the case when f is convex. When f is strongly convex, this rate can be improved as we have seen for the project gradient. You have the same rate. So any result for project gradient can be generalized to the proximal version of the method. So let's see the proof. You can also follow the proof we gave for the project gradient by using some property of the proximal mapping to replace the corresponding one for project gradient, for projection, for example, the non-expansiveness or some other properties. But let's see another proof that is more intuitive, because this will connect the method with the proximal point method in general. So let's rewrite this step. Because this is a proximal mapping of H, so this is an arc mean, right? This is an optimization. Here, this LF this is a linearization of the function f at the point xk evaluated at x. From here to here, you need to do some algebra, but it's just the algebraic manipulation, so I'm gonna skip this step. But this is really doable. You take the gradient of this one and take gradient of this one, and then that's going to be a gradient step here, and the proximal mapping comes from the h function here. So I leave this step for you to check. And from here, we are going to use the optimality condition. So if we ignore the last term, this is just saying that xk plus 1 is the minimizer of this one, right? So for any x, this is greater than this function value. By replacing x by xk plus 1. But actually, we can say more. There's more room to put another quadratic because this function, linearization is linear, so it's convex. H is convex. This is 1 over lambda strongly convex. So the summation of the three, this function is actually 1 over lambda strongly convex, right? And we have shown that for strongly convex function, you can say that f of x, so suppose this is an f function, f of x is greater than the minimum, right? This is the minimum, plus 1 over mu over 2 times x minus x star. This is your x star. Xk plus 1 is the x star to this minimization problem. So this is the additional quadratic that we can add. Okay, and using the fact that lambda is less than or equal to 1 over L. So 1 over lambda is greater than or equal to L. Right, we just replace 1 over lambda by L. And remember that for smooth function, the linearization plus this quadratic, you can check the gradient method lecture. I think it's lecture 3. So this linearization plus this quadratic is greater than or equal to the f at the point xk plus 1. And we also have h xk plus 1 plus this term here. And so this is greater than or equal to f plus h plus the quadratic, this quadratic. And on this side, we can further upper bound it because this is a linearization. By convexity, this is less than or equal to f of xk. Sorry, fx plus hx and plus this quadratic here. Right? Now we have this function. So this is like 5x plus this quadratic greater than or equal to 5xk plus this quadratic. Okay? But the function, the point x is undetermined. So we first take x to be xk. Then this term becomes 0. So what's left on the left is just f plus h of xk. On the right-hand side, this term becomes xk plus 1 minus xk. And this is just f plus h of xk plus 1. So this shows that the function value is actually decreasing, right? With one step of the proximal gradient, you can show the function value is decreasing. And if you take x to be x star, you will have f plus h x star right? And now we rearrange the term. We have basically this holds for any k. So let's just do a summation for k from 0 to some capital K minus 1. And then rearrange the term, you will find that summation f plus h xi minus f star I from 0 to k minus 1 This is just by rearrangement. And on this side, we can further show this is greater than or equal to, because this decrease in property. So this is greater than or equal to k times f plus h xk minus f plus h x star. So dividing the whole thing by k, we have the final conclusion. Okay, I think we are out of time. So this concludes the lecture on proximal gradient. Next time, we are going to talk about a faster way to solve this composite optimization problem, that is accelerated gradient method. Okay.